Welcome to the first video of Unit 2. In this video, we're going to talk about electron configuration, which is basically the order in which electrons fill in an atom. Now, as always, you guys are going to need a notebook and something to write with. And once you have all of those, let's start. So again, the objectives for this video are fairly straightforward. We're going to talk about two different methods by which we can describe how electrons are actually placed into an atom and how we can locate them. Now, before that, I'm going to go over a little bit of review of what you already know. I'm going to extend the model that you've been using a little bit, and then I'm going to go over some rules. All right, so let's start off with our review. All right, so what I have here is a Bohr diagram of an aluminum atom. All right, aluminum has 13 electrons, and what you know from previous experience is that the electrons will, I say quote unquote orbit, they don't actually orbit the nucleus in specific amounts or specific energy levels, right? So those specific rings, first ring, second ring, third ring, and so on and so forth. We call those shells. Now, each shell can hold a specific number of electrons. The number of electrons a shell can hold is equal to 2n squared, right? So the first shell, if n equals 1, can hold 2 electrons because 1 squared is 1 times 2 is 2. The second shell can hold 8 electrons. N equals 2, so 2 squared is 4 times 2 is 8. The other key thing is that electrons, as they gain or lose energy, can transfer between those shells. Right? So I can take an electron that's in the second energy shell. If I give it an amount of energy equal to the difference between those two shells, I can get it to jump up. And then if it loses that same amount of energy, it can go back down. So electrons can transit between different shells depending on whether they gain or lose energy. Right? So there are a couple of different refinements we have to go over. The first refinement that we need to go over is that electrons aren't just in these shells. We can actually further divide these shells a couple of different ways. The first thing we can do is we can divide them into what are called subshells. Now, subshells are given letter designations, and their letter designations are S, P, D, and F. So if you guys remember from the hotel pogle that we were doing, you had sunny rooms, you had pink rooms. That's your S, that's your P. Each of these different subshells has a different shape. S subshells are spherically shaped in 3 dimensions. P subshells are shaped like dumbbells. D's kind of like flowers. And F's are kind of weird and don't really draw well on 2-dimensional surfaces. Now, this chart right here will tell you for each energy level what subshells that energy level will have. So the first energy shell can only have an S sublevel. It's small, so it's only allowed that one subshell. Every time we add an energy shell, we can add another subshell to it. So second energy shell has both S and P. So again, if we go back to that pogle, the first floor only had sunny rooms. The second floor had sunny rooms and pink rooms. And as you go up, the third energy shell gets S, P, and D. The fourth gets all 4. And as you go past energy shell number 4, you keep all 4 of those as you go. We can also further divide those subshells, just like the bunk beds that you had in the pogle. Right? So those bunk beds are called orbitals. Each different type of subshell has a different number of orbitals in it, just like sunny rooms and pink rooms had different numbers of bunks. Right? So the sunny room only had 1 bunk, the pink rooms had 3 bunks. S subshells have 1 orbital, P subshells have 3 orbitals, D's have 5, F's have 7. And just like bunk beds, each orbital can hold 2 electrons, just like a bunk can hold 2 people. Right? So all the stuff that we did in the pogle, this is kind of how it applies to doing electronic structure. So we will break up these energy shells into subshells, break those subshells up into orbitals, and each of those orbitals can have up to 2 electrons or 2 people in that bunk. Now I'm going to go over the 3 rules. In the pogle, we did a good job of determining what those rules are, but this is just going to give you the notes version of this. right? So the first rule is called the Pauli exclusion principle. Whenever an orbital has two electrons in it, they have to spin in opposite directions. Now, when I say opposite directions, we're usually going to draw our arrows pointing up or down, but it could be clockwise or counterclockwise, north or south. Any opposing signs will really work. Our second rule is the Aufbau principle. Aufbau principle, lowest energy subshells fill first, then you go higher and higher. So just like trying to fill in the hotel or the boarding house, we put people on the first floor, then we put them on the second floor in the sunny room, then second floor in the pink room, because we want to make sure that the people have to walk up the least amount of stairs possible to get to their room. Electrons work the same way. And our last rule is Hunds Rule. This says that for any subshell, every orbital gets one electron before we double them up, right before we start pairing them. So again, from our POGL activity, we put one person in each bunk, so we fill the bottom bunk of each one before we came back and paired people in bunks. Same thing. We want to make sure the people are as spread apart as they possibly can be. Right, so these are the three rules that we're going to work with. Now, this next slide, I'm going to give you a diagram. This first diagram you don't have to draw. I would recommend not doing so, but it should look somewhat familiar to you. Right, this first diagram is an energy level diagram based on the energy of each subshell. Now, this should look somewhat familiar to you because, again, this works the same way the boarding house did. The lowest energy is the first sunny room. Then above that was the second sunny room, then the second pink room. Then we had the third floor sunny room, the third floor pink room. Right, so this right here just shows the energy of each individual subshell. If we go from bottom to top, we'll figure out the order that they fill in. Now, one thing I should probably point out here is once we start getting into D and F sublevels, things start to get a little bit weird. All right, so once we get into D and F sublevels, they kind of mix up a little bit. Now, instead of drawing this, what I'm actually going to have you draw is this one. This is what's called the filling order diagram. Basically, what you do is if you start at the top of this diagram and follow the arrow, and then once you get to the end of an arrow, you go to the beginning of the next one. And if you just keep following that from top to bottom, that tells you the exact order that these things fill in by energy. So pause this, take a moment to write down this chart, and then once you have it, unpause the video and we'll pick it back up. Our second rule was Hunds Rule. Hunds Rule, again, remember, says that we give every orbital one electron before we go back and pair them, right? So here we're going across our 2p sublevel. So we give the first orbital one electron, then our second electron goes in the next empty orbital, then our third electron goes in the third empty orbital, and after doing our third electron, now the fourth one's going to come back and it's going to pair. Right, so this is the example of Hunds Rule. And notice for our oxygen that when we paired these electrons, these two arrows are spinning in opposite directions. The arrows are pointing opposite ways.